Hi, welcome. Thank you all for coming. I should apologize for the fact I only learned I was doing this at about 2 o'clock yesterday, so it's pretty much a rerun of last year, and I might not be entirely practiced, though I do talk about this stuff a lot, so hopefully it'll be okay. The slides include some fairly small text that you might find difficult to read. There is a URL on here which claims you can get the slides, and you will be able to do that, but not at this moment. But if you, and I'll read it out because it's tiny, but if you go to the same thing with 2017 in it, you can get last year's, and there are only 2 slides that are different. So the URL is tdda.info/pdf/tdda-tutorial-PyData London and then for last year's 2017.pdf. So if you're struggling to read these, those might help. If you haven't already done it and you do want to follow along, there are exercises and there are things to do during the session. You should install the tdda library, which you can get from PyPI with pip install tdda. Or you can get it from GitHub if you prefer from the tdda account, and the library is called tdda. So, do interrupt if I'm not clear, which will almost certainly be the case. The whole thing's supposed to be very informal. So, today we're talking about test-driven data analysis, and I'm going to start off by trying to motivate that for you. And it's as much of a surprise to you how it's going to start as it is to me. I mean, it's much of a surprise to me as to you. Right, so the idea, yes, of course, it's called test-driven data analysis, taking its inspiration from test-driven development. And the idea is that we need to take the ideas of testing from test-driven development, this idea that before you write code, you write tests, and then you run the tests and they fail, and then you correct the tests by implementing code. We need to take that idea and inject a bit more of that idea for trying to make software correct into data analysis, where there's typically a lot less testing, in my experience, certainly a lot less systematic testing. And one of the interesting challenges with testing data analysis as opposed to testing software is I think it's a lot harder because mostly with software, with many kinds of software, anyway, we kind of know when the answer is right. It's kind of obvious, it's does it crash, it's does the interface do the right thing. Sure, where there's maths involved, things can go wrong, but it tends to be more obvious whether things are working. Whereas with analysis, we have to be concerned not only with is the software or the implementation of our analytical process in whatever set of tools we're using working, we also have to be concerned with the meaningfulness of the analysis. Is it producing answers that are going to be interpreted correctly? We have to be worried about whether the input data is valid, because we all know garbage in, garbage out, but it's not really good enough for us as data scientists to say, well, you feed bad data and it's not my responsibility. I think it kind of is our responsibility, and we have to be responsible for helping people to interpret correctly. So it's with all those things in mind that we've developed this idea of test-driven data analysis. And I guess the way we think about this is that almost always these days there's some kind of a development phase where when you're developing analysis, you always work in the context of a data set. You're almost never doing it without data. And inevitably, the data that you use to develop the process affects the way that you develop the algorithms or the processes. And there are lots of things that can go wrong during that development phase. The first of which is, you have to choose how you're going to tackle your problem. And you can fail to understand all sorts of things. You can fail to understand the data correctly, you can fail to understand the problem domain, or you can have an insufficiently good understanding of the algorithms and what the requirements of those algorithms, the statistical or any other aspect of them. And when those things go wrong, we like to classify things, and we call those kinds of errors of interpretation. So things can go wrong there. And then you have to implement your process, which, in our case, might be a question of writing Python code, but it might just be a question of putting something together in Excel or using R or SAS or whatever. And unfortunately, some of us are capable of making errors at that stage too. Traditionally, those obviously are known as bugs. But we call them errors of interpretation just to keep the error of thing going. And I guess the idea is if you get through both of those stages without making mistakes, then you get your initial success. And 20 years ago, that was pretty much what people who weren't then called data scientists had to do. But now it's typically worse than that, because now typically when we develop analysis, we want to put it into some kind of operation. We don't want to just run it as a one-off thing on one particular set of numbers. We want to have something that we can apply again. And even if we don't believe that when we're developing it, almost always after we've finished it, one of the following things happens. Either someone tells us that data you analyzed, yeah, that was the wrong data. Could you just do it again on the corrected data? Or, your boss comes over and says, yeah, that thing I said, could you just do a quick and dirty once-off? Could you just do it again on this month's data? Because it was really great. And so you almost always end up with this need to be able to use whatever you developed on a new set of data, which is potentially its own challenge. When you do that, there's a whole new set of opportunities for things to go wrong. Because now you have to run the analytical process. And it's possible to use the software incorrectly, to type the wrong options, to use the wrong version of the software, to fail to understand that it's a Python 3, not a Python 2 package, or a Python 2, not a Python 3 package, or that it, whatever. And when we call those errors of process, when things go wrong there. Perhaps the subtlest one is that, as I emphasized, it's almost impossible to develop most analytical processes without making assumptions about the data. And those assumptions shape our analysis quite strongly. But quite often those assumptions turn out not to be true for all the data that we ever put through the system. And so sometimes even when it produces numerically correct results that are executing the algorithm that you wanted, the assumptions that you had implicitly made in producing the algorithm turn out to invalidate at least the interpretation of the answer. And when that happens, we call that an error of applicability. And the final thing, of course, is even if we don't make any mistakes anywhere along the way, we can still misinterpret the results. I used to share an office, when I was doing a PhD, I used to share an office with a guy who was a great one for staring at a graph and saying, yeah, I can see why it's like that. And I'd say to him, yeah, but you've got the graph upside down. And he'd turn it upside down and say, yeah, I can see why it's like that. It's very easy to get seduced by the beautiful output that we produce from computers and things, because it's all beautifully formatted and nicely colored and very plausible and exactly what we expected, that it's right, but it's not true. So probably you're sitting here thinking, I don't make any of these kinds of mistakes. I'm better than that. And you probably are. But it's quite sobering if you do buy into this sort of framework at all. Oh, sorry, the other thing that happens, of course, is you go around this last bit of it lots of times feeding more data sets in. You see, I told you I was out of practice with it. It's quite sobering to just put some numbers on it and think, I've put what I think are quite optimistic numbers on for how likely we are to go wrong. So I'm saying there's only a 20% chance we'll misunderstand something fundamental in the approach that we're taking. There's only a 30% chance that there'll be bugs in our software, which I think is fantastically optimistic. Now, and I'm talking about important bugs here, not ones that, cause a line break in the wrong place, but ones that cause the wrong answer to be produced. I'm assuming there's only a 10% chance that we'll screw it up when we run the software, bearing in mind that it might not even be us, it might be someone else running the software. A 20% chance that the data will have changed in such a way that it's no longer what we assumed when we developed the thing, and only a 10% chance that we'll misinterpret the results. And if all of that's true, the first time you run the process, you have a 36% chance of getting the right answer. Now, maybe you think all these numbers are incredibly pessimistic. Put your own numbers in. It'll still be scary. And, of course, the really good thing is every time you go around this process, you get a chance to screw up again. So there's a lot that can go wrong. So what we're really going to talk about today is test-driven data analysis, which is both a methodology, a way of thinking about how we do data analysis, data science, machine learning, whatever you want to call it, and also in the form of the open-source tdda library, a set of software that can help you with this. There's a set of proprietary extensions we have as well, but I'm not really going to talk about those. And there are sort of two and a half main ideas in test-driven data analysis. We're going to do examples and exercises on both parts. We're going to start with what we call reference tests, which are maybe the less exciting part, but definitely an important part, and then we're going to move on to talk about automatic constraint discovery and verification. So reference tests are kind of just like the tests that hopefully we're all used to writing in ordinary software development. So, you can compare those to particularly system or integration tests rather than unit tests. They certainly apply to the equivalent of unit testing too, but I'm in the minority of people who thinks that the integration tests, the system tests in all contexts are more important than the unit tests. Of course, unit tests are important, but I dislike the way everyone focuses on, not everyone, a lot of people focus on unit testing and don't really bother with system testing. But particularly for analysis, I think it's testing the whole system that's fundamentally important. So it's support for helping writing tests that are appropriate to data analysis, where, and what I would claim is that the usual way we're taught to do test-driven development is hard for data analysis, because the usual thing we're told is first write the test with the correct answer, then run the code, then run the test, and obviously it will fail because we don't have any code, and then implement the code to make the test pass. The trouble is most of the outputs that we generate in data analysis, a lot of them are things that we can't compute by hand. So unless we have another package that already does it, we simply don't have the option of, I'll just draw the graph by hand and check that it comes out correctly, or I'll just compute these 2 million numbers by hand. And so we kind of have to do it backwards. And another one of the things that's different is very often the answers are not the same every single time. And I'm not primarily talking about numerical instability or the fact that we use random numbers. I'm talking about even things like because they have a date in that changes, or because you use matplotlib and it turns out matplotlib uses random labels all over the place and reorders things because it pulls them out of dictionaries and all sorts of stuff that just mean the actual generated result isn't identical sort of syntactically to the one that you might have saved, even if it's semantically identical. So the first part is about providing what we call reference test support for writing tests that are useful for data analysis. And then the second part is all about automatic constraint discovery and verification. So the idea there is that when we're doing data analysis, we have data at all stages. We have input data, we have typically intermediate results, and we have output results. And all of those are things we should want to test. We should want to check that, at the very least, the data we develop the process with produces the same answer when we run it a second time and a third time. And we potentially want to check the input data, we want to check the intermediate results, and we want to check the output results. And a really powerful way of doing that is using constraints. And we can write those constraints by hand, but we can also get the software to find suitable constraints for us from examples. And that's what probably the bigger part of this morning will be about. So, any questions before we move on to start actually looking at stuff? I can hardly see you because I'm kind of blinded by these lights, but someone should shout if there is anything. I'm going to take it that we're good. So, hopefully you've all either done a pip install tdda or a git clone of the repository and then a python setup.py install. The library is Python 2 and Python 3 compliant. Obviously, you all know that you should be on Python 3 by now, even if you really don't want to be, but it should work either way. The library, I believe, runs on all platforms. It's true that we run it on Windows rather less often than on the other platforms, but we have done so, and last time we did it, it did work. And it's compatible with both unit test and PyTest, so you can use whichever you prefer. It's MIT licensed. There is documentation, standard Sphinx documentation, and you can see it. Oh yeah, not at that URL at all. It's on Read the Docs now, isn't it? It's at, right, so I will try and remember to correct this, but it's at tdda.readthedocs.io, not at pythonhosted.org, because obviously we've moved over to Warehouse since last year. And there is a quick reference sheet that's only slightly out of date at that URL there. I'll try and update that as well. Apologies for the fact this is, I know some of this is too small to read. So, reference tests. I've probably talked about this. So the idea is our analytical process is whatever that computes something or produces a graph or gives us a go, no-go, or tells our chatbot what to do or whatever. It takes inputs in the form of, the data and parameters typically, and it generates some kind of outputs. And the minimum idea for a reference test, the idea of a reference test really, and if you're not familiar with testing, don't worry about it, you can just start from here. The idea is, if you do nothing else, at the very least, record the inputs that you used when you developed the process, capture the process, preferably in an executable form where you just have to, conceptually push a button, type make, do some simple command to run the thing, and capture the outputs that you produced so that you can check at some future point when you come back to it that A, it still runs, and B, hopefully that it produces the same answer. And so the second idea is not only should you be able to look at the answer and see whether it's the same, but ideally there should be some kind of an automated way of checking that the result's the same. The equivalent of a diff or a compare or whatever for whatever your outputs are, and that's what we try to help with reference tests. It's quite closely related to the idea of reproducible research, which you may have come across in the academic community. Reproducible research it's more the idea of using other people to check that your stuff's right by making your data and your code available for other people to look at. One of the nice things about the reference testing approach is that even if no one else ever looks at your code, you can still get benefit from it because you yourself benefit over time from what you've done. Now, one of the things that sometimes people say at this point is, if I write my code and I put it there and I leave it and my data stays the same and then I run it again later, surely it's going to produce the same answer. What could possibly go wrong? At which point, hopefully, half of you burst into laughter because you've all experienced the fact that you wouldn't believe the things that can go wrong. Whether it's, that your operating system decides to do an auto-update, or you upgrade your Python, or you upgrade one of the libraries, or a helpful coworker upgrades something on your system. And that's before actually you did edit it. You just made a little tweak that couldn't possibly break anything, but turns out it's quite hard to make tweaks that can't possibly break anything. Or you get bit rot and the data's changed, or you're not running the version of the code you thought you were, or there are so many things that can go wrong that I guarantee if you do this, you'll find quite a lot of the time when you run the test, it won't pass another time. So this is valuable even if you never change anything. But in fact, you will change things because when, your boss, your client, whatever says, could you just run that thing again on the updated data, it will turn out that data has a different format, has a different distribution, has whatever. And things won't be the same. And then you'll make an adjustment to handle the new date format or the extra column or whatever it is, and that will break your original thing without you realizing it. So what's in the reference test library? There are things for comparing an actual string that you've got in memory or in file, one that you've produced from your code with some expected string that you've stored away in file. There is the ability to exclude lines with particular substrings, like a date or a version number or something like that you can specify either as a literal or as a regular expression. There's the ability there are sort of hooks that allow you to put functions into pre-process output. So if there are things that you know are going to vary that you don't care about, you can take them out by hand in code, by writing a function that manipulates the thing before it tests it. It can write the actual string produced to a file when it's different, so that if it turns out something's changed, you're not trying to compare something on the screen with something that's in a file. It's written a file for you that you can then use diff or opendiff or visual diff or whatever to understand what's going on. It will tell you what the diff command you need to execute to do that is. It will allow you to check multiple files in a single test and report all the failures rather than falling over at the first one. And if you ever do that thing you're not supposed to do, but we all do, where you loop over a whole load of test cases in a single test, particularly if there's lots of expensive setup. And the other thing it can do, which turns out to be super useful but easy to abuse, is if you do find that the result has changed, but the reason the result has changed is either that some formatting thing's changed that doesn't matter, but it's the new way of doing things, or it's changed because your original test result was wrong and you've now fixed it, it will automatically update. It can automatically, when you tell it to, update the reference results that it's comparing things to with the existing ones. Now, obviously, if every time a test fails, you tell it just write the new results to the reference output, then you'll get no value out of the system. But if you carefully check them by hand and only tell it to rewrite the results when you've really, hand on heart, promise you've checked that the new answers are actually better than the old answers, then this can be tremendously powerful. So there's a set of methods that are very much like the unit test methods in the case of the unit test support. So you can say self.assert string correct, and you can give it a string, the string that you want to test and the path for the file, with the file in it that's got the expected string. You can directly check two files if you're generating files. You can check sets of files, and all the dot, dot, dots indicate there are lots of extra parameters you can put in to say, do you want to strip the strings beforehand? Do you want to this, that, and the other? And that makes it sound like we're just talking about strings, but we're not. There are things for checking data frames. There are things for checking numbers. There are all sorts of things, which I can't remember whether we talk about later. But anyway, this is the point where you get to do some work. So if you have the library, it comes with examples. So if you go somewhere you don't mind creating some directories, and then you type tdda examples, it should copy 3 sets. It should create 3 subdirectories for you for the different kinds of tests we'll be doing today. And the ones we're interested in, first of all, are in reference test examples. So hopefully if you do something like cd/tmple, twiddle/tmple, wherever you want to put things, tdda examples, and then go into that reference test examples, you should find 2 files, stringresult.html and fileresult.html, which you can look at. They're just HTML files. So you can open them in a browser, or you can... if you're the sort of person who likes reading HTML, you can read it. And then if you are not philosophically committed to PyTest, you can go into the unit test subdirectory and run Python test using reference test case.py, and hopefully the tests will pass, and then we'll have a look at what it was doing. Or if you're more of a PyTest kind of a person, go into the PyTest directory and type PyTest. So I'll give you all a moment to do that. So actually maybe I'll do the first bit of that. Not like that. So reference test examples. Right, and then in reference, I think, there we are. So if we look at the file result, it's that incredibly exciting web page there. And if we look at the string result, it's that similarly super exciting web page. So, and what I claimed is that if you run, what did I say? That if you run test using reference test case in the unit test subdirectory, there isn't a unit test subdirectory. Excellent. Then everything passes. 5 tests pass. Has everyone who wants to succeeded in doing that? You're all very quiet. I'm going to take that as a yes. So the interesting thing about this is that the result that this produced was not identical. So let's have a look at test using reference test.py. So it's got some of the usual boilerplate stuff at the top for handling Python 2 and Python 3. And it's got various tests. So this first one, that's a data frame one. Okay. Example string generation. So that's what we're looking at, I think. So we have a function that generates the string, the HTML page, in memory, which we assign to actual. Actual we pass in together with stringresult.html. And that stringresult.html, the thing's set up so that it knows that should be in that reference test subdirectory. There's a directive in there somewhere to tell it that's where it is. And we're telling it to ignore the substrings copyright and version, because there's a copyright line that changes each time we update the library and a version number that changes each time we update the library. And they're different. And then we've got a sort of file example as well, where now we're generating this file result.html, and again, we've got the same exclusions. So if I compare, God, you can tell I can't remember how to do this. If I compare reference, if I compare something or other, I wonder where it generated it. Oh, maybe you're supposed to run generators first. Well, I wonder where it's generated the results. It's all a fix, folks. It's not doing it at all. Generate file and write it to HTML. And HTML was... No, right, the HTML to path. And what was path? Oh, path's called from reference test. And it probably cleans itself up. Outpath and outpath is out there. Oh, it's writing it to tdda is the point. Right. So here's the good thing to do. Edit the generator to change what it produces. Yes, of course, edit generator. So if you take that generator code, yes, this is the thing to do. So the HTML is generated just directly from that big multi-line string literal. If you edit that code and change, say, the page title or the H1 or something like that, then obviously you'll get a different result and the test should start failing. But if you edit something like the version string in there, that shouldn't cause the test to fail. So that's why I would suggest you first try changing that 2016 copyright notice to, say, 2018, check the results still pass, and then change, the title or something to something else, and now the test should fail, and it will give you the thing. Sorry. In my defense, I didn't know I was doing this till yesterday, and I would have tried it. So I'm going to do that while you're hopefully doing it yourself. In a tiny little window that you can't read. So, reference tests. Here we go. So, I'm first of all going to change that 2016 to a 2018, and everything should still be fine. Everything still passes, but when I change anything more meaningful, we get a failure, and it gives us the diff command that we need to see the failure, which we can run. And so we see the copyright and versions are different, but that's okay. The test was told to ignore that. But we can also see the KKK on the line, and obviously if we do something nice like an open diff, or whatever your visual diff command on whatever platform you're using is, so the same thing but just add open, we see visually rather more clearly what's changed, which is exactly the KKK that I put in. Everyone succeeding with that? Anyone failing with that? Does it all kind of make sense? Do you get why this might be useful? Okay. Would anyone like more time to play with that, or shall we press on? So that's the general concept with reference testing. Let's find out what the slides say we're doing next, and we'll decide whether we want to do that or whether we want to move on to constraints. Oh, look at that. There are instructions. Modify generators.py. There you go. Run everything again, see a failure, check the results. Yes, all that stuff, exactly. Yeah, so that's fine. So then the other sorts of things that are in the reference test library, as well as things for checking strings, there's something to check a data frame where you can specify whether you want to check all the columns or just particular columns. You can specify numerical precision. You can probably specify a bunch of other things, but I can't remember. You can specify a diff. If you have a way you like comparing data frames, you can specify a diff command for doing that. It can check CSV files as well as data frames, provided that the CSV files are readable by Pandas CSV reader with the sensible options that I'll talk about later that we tend to pass to that. You can choose whether you care about the types of the columns. So one of the things any of you who use Pandas will know is that it's got a fairly flexible attitude toward types. And if you, for example, take an integer column and throw a null into it, suddenly you might find it's not quite such an integer column anymore. It's become a real column and all that kind of stuff. You can tell the library whether you care about that stuff. You can tell the library whether you care about the order of columns in a data frame. You can choose to ignore the actual data in particular columns. You can choose the precision for your floating point comparisons. And again, you can get it to automatically rewrite files if you like. So all of that stuff's in there. I don't think we have exercises for all of that, but you can certainly play about with it. So a bunch of methods. And again, I'm showing the unit test ones. There are the obvious PyTest equivalents of these as well without the selves. So for asserting that a CSV file is correct, or a bunch of CSV files are correct, or a data frame is correct, or a bunch of data frame correct, or data frames equal. Okay, that's interesting. Oh, so the first one is for checking a data frame against a CSV file, and the second one is for checking a data frame against another data frame that you have in memory. So there is an exercise for that. Oh, well, let's do like it says. Let's try the data frame exercise. So apparently there is... So same... Oh, no, so it's the same exercise. The point is we can look at the data frame being generated with this two-line program. Oh, let's do that. I'm glad I wrote all this stuff down. So let's try running that and see what it does. So that's the data frame it's generating. Okay. And so run the tests. We've already done that. Modify dataframes.py to change the precision from 3 to 2. Okay, well that'd screw everything up, wouldn't it? So presumably that's in dataframes.py, and there's presumably a precision somewhere. There you are. We'll change that to 2. And so now we get 2 digits in that S column as opposed to 3. And now if we run the test... we get a failure, which we could look at, but presumably, I'm imagining there's going to be a punchline that if we tell it to right. Oh, and so the idea here is let's show you rewriting the output. Yes. If we say this is actually the result that we want now, we want to, we've changed our mind and 2 decimal places is the answer that we want as our reference. What we can do is run the tests again, but now say either minus capital W if you're lazy like me, or if you're not a lazy person, you can say write all. And that will cause it to regenerate all the reference test results for us. And therefore, if I run the tests again without the write all, they pass again because we've updated the reference results. So, sorry, that was all slightly mad because I don't know what I'm doing. But hopefully that all makes sense and you'll find it useful. One very cool new capability we've added recently. I guess the thing that you're taught when you learn testing is that your test should take about a nanosecond to run so that you can run them all the time. We find that quite often our test suites take several nanoseconds to run, sometimes even minutes or hours to run, depending on what we're doing. And again, in the context of concentrating more on integration and system testing and on generating large, complex analytical results, even if you scale down the data, that's often quite hard to avoid. So it becomes particularly useful to be able to run individual tests or individual subsets of tests. And you can obviously do that by putting the test name on the command line, or, my favorite technique of sticking an A in front of the test method so that it doesn't get picked up. But we have a nice capability now in the very latest version of the tdda library, which is 0.5.12, and if you picked it up as 0.5.11 yesterday, it's not there under this name yet, but if you update it, will be. We have this very nice ability to tag tests, and what that means is that if you run with either -1 or minus tagged on the minus tagged on the command line, it will run only the tests that are tagged. And what we mean by tagging is if you import tag from the same place as reference test case, if you use the decorator @tag in front of either a test or a test class, that will tag that class. When you run with -1, it will only run the tagged tests or the tests in tagged classes. And what happens if you have a lot of test files with that is you find you now don't know where the tagged ones are. So to avoid you having to grep, you can also say -0 or -is tagged, and it will tell you which of your classes in which of your files are currently tagged, so you can go and update them and remove them. And that sounds like a really stupid, tiny bit of functionality, but it saves hours and hours and hours if you use this stuff. We've had a very similar capability in our commercial software for years in a slightly less elegant form, actually. And we use it absolutely all the time. It's particularly good when you're developing some new piece of functionality in the context and it's got a big test suite and you just want to keep running one test over and over again. It's surprising how simple these things, how powerful these simple things can be. Okay. Any questions before we move on to talk about constraints? Yes.
Could you give a few examples of where you've used the data frame and like multi-function functionality in practice?
Yes. So the awful truth is we don't use data frames very much because we've been doing this stuff so long that we have our own analytical software that has the same sort of structure as a data frame that we developed about 10 years ago and that we're still using. So conceptually we're doing very similar stuff. We just have a version that doesn't use literally a Pandas data frame. It uses a Miro data set, which is sort of our equivalent of that kind of thing. And we use that absolutely all the time, both when we're developing the software. So whenever we make any change to the software, we're constantly checking that we haven't broken any of our existing functionality. But also when we're doing anything for clients, we really are quite religious about doing this stuff. We don't follow the test dogma in the sense of writing the tests first, because as I've explained, we typically can't do that because we can't generate the results until we've written the code to do it. But we really do pretty much as soon as we've got something that we think is working, we capture the result, we build it into a test, and then we keep running that. And we actually have it running on continuous integration servers so that twice a day, the whole test suite for all of our client projects for whom the data hasn't expired yet, but during the whole course of a project, we're running the tests as we build up the thing as we go. And, the particular kinds of projects we're doing that with, we've done a lot of work with Skyscanner over recent years on travel, so we've been doing things like modeling the surcharges that their partners put on flights. We've been building anti-gaming systems for them. We've been looking at their complaints and building reporting systems for their complaints. We do credit scoring work, so the same thing again, checking that given a historical file that even particular models train the right way, and more particularly models that we've already built are producing the right results that we expect, and that when we update the model, we update the reference results for that and check that that's good. So we're doing it absolutely all the time. Even when we're not doing it, our integration servers are doing it for us. Does that help?
Yeah.
Hi.
If you haven't generated your reference yet, then when you run the test, does it automatically create the reference file that's
Yeah, if you run it with minus capital W or minus right all, it will generate it for you. Yes.
I guess it could be useful if it did it without having to minus W
I think we might regard that as just a stage too far in terms of we're trying quite hard to get the balance right between making it easy for it to take the work out of generating stuff when you know that you want it to do that, but not making it so easy that you just constantly keep creating wrong results. Because to start with, the first time you generate it, it almost certainly won't be right. And I feel like if you just generated it as the reference result, that I feel like that might discourage you from going and actually checking it by hand, whereas the process, I can't emphasize enough, none of this stuff means you don't have to check it by hand. On contrary, you absolutely have to check that the stuff really is the right answer. It is true that even in advance of knowing that it's the right answer, it's useful to know that it's the same answer, because, unintentionally stochastic software is not great. But, it could absolutely be done. It would be an easy change, but I'm not sure it would be good.
How does it handle floats?
Well, precision, basically. So you can specify the number of decimal places. Well, number of decimal places you want to test it to. Obviously, what it's not trying to do is handle the fact that if you train a model with stochastic inputs or stochastic weights or something, that you might get a completely different model in different cases. I'm not sure whether that would be a desirable thing to do or not, but I think that's not one of the things it's trying to do. It is trying to handle, and in fact, floats are an interesting question anyway, because although there's sort of this idea that you should never test floats exactly because they're floats, they're sort of arbitrary. That's not entirely true. On any given platform, you should get identical results when you run the same code, even when it's generating floating point answers, as long as you fix any seeds if you're using random number generators. And I've been quite surprised over the years, now that virtually everything's standardized on IEEE floating point notation. I've even implemented things like in Python 2, in Python 3, in Postgres, and got identical answers to full precision. Now, in the case of databases, obviously you have lots of choices of floating point representation, but if you choose the right one, you can certainly do like 10 decimal places of precision and things work. You can go much further than a lot of people think you can go without anything changing. And as I say, for a particular code running on a particular computer, it should definitely produce identical results with identical inputs in the absence of stochastic stuff. Okay, let's move on and talk about constraints. Yeah.
Easily overrode the reference table area. What if I have, let's say, maybe a different model that actually still needs it? Is it like a way of telling as part of the test another process depends on this reference table and you shouldn't override it?
Okay. Okay, so that's an interesting question. The question, if people couldn't hear it, was what if something else depends on that reference output as well? Is there a way of telling it not to overwrite it? I think the real answer is no. I mean, the way of telling it not to overwrite it is not to use the -W or -right all flags to tell it to overwrite it. But no, there's not a way of... There's nothing in the library to understand dependencies and understand that you shouldn't just update a particular reference result or whatever. That's something you would have to manage externally. But it's an interesting thought. Okay, let's talk about constraints.
So
So, here's a controversial statement. Very commonly, data analysis uses data tables, particularly if you're not doing text mining. Data frames or whatever as inputs, as outputs, and as intermediates. And there are almost always things we know ought to be true about this data. We might not always make them explicit, but there are almost always things we know. And in principle, we could write down all these expectations as constraints and check that they're satisfied, that the inputs satisfy what they ought to satisfy, that the outputs satisfy things they ought to satisfy, and so on. But life's too short, and even if life weren't too short, we're human, we're not very good at writing down correct answers ahead of things, notwithstanding the unit testing dogma. So the big idea with this constraint generation stuff is, since we're not very good at it, and since it's really boring, and since computers are really good at boring things that we're not very good at, why don't we get the computer to generate constraints for us? And then we can verify against those constraints. And if it generates the wrong constraints, at least we get a starting point that we can edit. And typically, in my experience, people are much happier to spot mistakes in something and edit it by hand than to be presented with an empty editor and, knock yourself out, type some JSON. It's really good as long as you remember the commas and the non-commas and the stuff. So what are some examples of constraints? Well, if you've got ages of human beings, they probably shouldn't be negative, and they probably shouldn't be bigger than 150 or maybe even 110 or something. Probably ages ought to be integers or at least numbers. If you've got a master table with customer IDs in it, then probably those shouldn't be null, and probably if it's a master table, they shouldn't be repeated. If you've got a credit card number, it probably ought to have 16 digits. It'd be nice if it allowed spaces, but apparently that's beyond the wit of programmers, so we don't allow those. If you're a biologist and you're looking at DNA, then probably the bases ought to be mostly CGs, A's, and T's, and so forth. Dates, all the usual stuff. In principle, even looking at distributions and things, if you've got human heights, you probably have some idea what the range of those heights ought to be and what they ought to look like. So there are constraints that you can put on individual values and individual columns. There are also constraints that operate more at data set level. So maybe your data frame or your data set or your database table or whatever has to include particular columns. Maybe it has to have a particular number of records. Maybe fields are supposed to be tagged or indicated in some way. Maybe it's supposed to be sorted in some way, like data sending or whatever. And there also might be constraints between fields. So a very common one, if you have start dates and end dates, for example, in many cases it's nice if the start date isn't after the end date, but in real data, obviously, it often is. If you have, God, you can tell I'm a physicist. If you have columns representing force and mass and acceleration, then probably there ought to be a Newtonian sort of relationship between them, given that F equals ma. If you've got a bunch of favorites and only one of them's allowed to be 1, then if you sum them, you should get 1, and so forth. So there are lots of things we could specify, but that are a bit painful for us to do by hand. The kinds of constraints that the tdda library understands are min and max constraints, and in the case of strings, min and max length constraints. Sign constraints separately from min and max constraints. So the idea there is, it's all very well you can specify a min and maximum range, and obviously that implicitly says whether it's allowed to be positive, but it's sort of a more significant change if something that was always positive previously turns negative. So we redundantly store constraints about sign, or can redundantly store constraints about sign. We can specify whether fields are allowed to be null. In fact, we can specify the maximum number of nulls allowed in a field, but usually that's either 0 or unspecified. We can specify that a field's not allowed to have duplicates if it's not. I've talked about min and max lengths. And the most powerful thing is we can also, well, particularly in terms of generation, is we can also specify one or more regular expressions that string fields are supposed to represent. And when we come to automatically generating them, we can automatically generate regular expressions from examples, which is why I talk about kind of 2.5 bits of functionality in the library, because that's sufficiently different that it's useful even if you're not using the rest of the stuff. And we call that functionality RexPy. So, those of you who have laptops and are following along, you should already have the examples if you go to the constraints examples rather than the reference test examples that we were in before. Oh yes, we're working with the periodic table. We're working with the periodic table as it was on Wikipedia about 10 years ago, so it's a little bit out of date. So if you go into the constraints directory and run Python elements discover92.py, what will happen is it will generate a JSON file called probably elements92.tdda. In fact, yes, elements92.tdda, which is a JSON file that contains constraints that are true of the first 92, i.e. the elements up to uranium in the periodic table. So, for those of you who are not following along, I will do it as well. I've probably done it before, so I probably have the files, but I'll run it. Elements, discover, underscore, discover, 92.py. And so that's written elements92.tdda, and what that looks like is this. Oh yeah, no, that is what it looks like, that's right. So it's just a nested set of dictionaries with a fields top entry and then an entry for each field. And so you can see Z, which chemists among you will know is the atomic number. It's kind of like a UID for chemical elements. Start at 1 with hydrogen, go up to 92, well, used to go up to 92 with uranium, now go up to at least 118 with what used to be called ununoctium and now has a name I don't know. And so it's determined that Z appears to be an integer field, that it is an integer field, in fact, I wonder what it used as. Let's have a look at the code and see what kind of data it used. No, that is not right. Elements discover 92.py. So it read a CSV file, in fact, using Pandas CSV file reader. There's a command line version of this we can use as well. We'll have a look at that. When you install the tdda library, it installs a tdda command, which I guess is what we use to get the examples. But there is also a tdda discover, a tdda verify, and a tdda detect. So this thing, anyway, is starting from a CSV file with the elements in it, turning that into a data frame, and then writing out this elements92 that we're looking at. So it's determined that the atomic number is positive. It would say non-negative if it had zeros in it, but it's not. It's strictly positive. Minimum of 1, maximum of 92, that it doesn't have any nulls in it, and it doesn't have any duplicates in it, all of which is pretty much what we would have said. Now, obviously, if we look at that and we said, are those really the appropriate constraints for atomic number? Well, they're not. Atomic number isn't supposed to cap out at 92. It can certainly go up to 118, and who knows what the limit really is. So we would probably either want to edit that to increase it to something big like 130 or 118 or whatever we think, or take it off altogether. But the point is we've got a starting point to work from. Then we've got the name. You can see it's put in, it's noticed that it's a string, its minimum length is 3 and its maximum length is 3. It's doing this completely stupidly. It's just looking and saying, well, what is the shortest string? What is the longest string? It's not doing anything clever until it gets to regular expressions. And we haven't told it to generate regular expressions. Because that's more expensive than the other parts, you have to explicitly tell it to do that. We'll do that in a minute. That it doesn't have any nulls and that it doesn't have any duplicates. And so we carry on down. We've got various things. But what you will see is, a lot of them don't have the duplicates, the no duplicates constraint. Some of them don't have the nulls constraint. It will, in the case of fields that only have a single null, it will actually generate a max nulls equals 1, because that's kind of a special case that sometimes you're allowed a single null in a field as a kind of catch-all value, but not multiple nulls. Whether that's appropriate or not, I'm not sure, but that's the way the library works at the moment. And so this is just an ordinary JSON file. You can go in and edit it. We'll probably even let you do that in Excel one of these days, but we haven't done it yet. So I suspect what we're supposed to do next is to run a verify. Yes. Oh, and so the other thing is you can see that on here we've also got the command line version of that. So let's do that. If we say tdda discover, and then we give it our input file, which is test data /elements92.csv, and we tell it where we want the results to go, which will be to elements. I'll just call it elements.tdda actually, so we can see it's different. That will again generate that same file, hopefully. It didn't generate the same file because, of course, JSON isn't ordered, so you can get different orders. But if we, so we could use the reference test library to filter out that kind of difference. But anyway, we're not going to do that. But it's generated semantically the same, an equivalent file. So the next idea is what happens if we verify that. So if we verify the same data that we built the constraints on, in almost all circumstances we expect that the verification should pass because the software is working correctly, we built constraints that are supposed to be true. So the idea is, to make it clear, the idea is that when you run the discover process, usually you should be running it on known good data. You can run it on data that includes bad data as well. It's just that then you won't necessarily get all the constraints you want, or you might get inappropriate constraints, and you'll have to edit them by hand. So it's more set up for running on good data. So the sort of slightly weird fiction here is that the good data's elements up to 92, and then these other weird ones are coming in, and we'll learn what happens. So if we run a verify, which we could either do in code, or again we can do from the command line with tdda verify. So if we verify the full 108, well, if we first of all verify the data we built it on with the constraints that we built, then we get 72 constraints pass, none fail, which is good. But if we run it over the full 118 data, then we get a bunch of successes and failures. So 57 of the constraints still pass, but 15 of them fail. And you see the ticks and crosses indicate which ones passed and which ones failed. So on density, for example, the max changed, which is not surprising. Some of the transuranic elements you would expect to be denser. And there are nulls because we don't know the density of an octium, probably because, well, it's only stable for like a fraction of a second. So we can get the summary information like that. We can also, something that wasn't true last year but is true today, is if instead of verify we say detect, then it will actually, and we specify where we want it to go, it will write out the failing records. And by default it just writes out the that's interesting. It writes out a not very helpful record number. Oh, yeah, no, it really shouldn't have been that. Okay, so maybe that's something we have to change. Happily, if you say, oh, brilliant. If you say minus output fields and minus per constraint, which in fact you almost always do, and you tdda detect test data. That's almost always true, thank you. Then we get the same thing, but now in bads.csv we have the failing elements which start with helium. What on earth is helium doing in there? So mostly there might be a little issue that we might have to address in this new detect functionality. Mostly you'll see it starting at 93, 94, 95, so it is the correct ones, but we appear to be writing out one extra record that shouldn't be failing. Well, that's embarrassing. But anyway, that's conceptually what the detection functionality does, and if it is wrong, as it very much looks like it is, we will get that fixed probably by the end of the day. So that's powerful. Is anyone having any problems running that, apart from possibly generating completely bogus results? Okay.
I have a question.
Yeah.
To what extent is this compatible with collections of data sets? So suppose that my data sets are structured in a certain way, but I'm not super sure whether all my fields are going to be in all of my data sets.
Oh, that's fine.
Can I do something?
Yeah, so the default way that it runs, I think it will report missing fields, but it won't cause things to fail because of missing fields. But I'm fairly sure you can tell it whether you require all fields or, if it should regard a missing field as a reason to fail the tests, or whether it should play that through.
Okay.
So yeah, it's quite flexible in that way. And by default, it doesn't care about column order and stuff like that. In fact, not just by default, it doesn't care about column order. So it matches on name, and so if they come out in a different order and stuff like that, that's fine.
So that sounds like for the verification process, but for the constraint generation process, can I also feed in a collection of data sets there?
You can't at the moment. You would have to combine them, but that is an obvious thing to be able to do. Yeah. And I mean, another obvious thing to be able to do that we haven't supported, that we don't yet support, is taking two generated sets of tdda files or more and combining them either by sort of taking the tightest intersection or the broadest union or whatever. The other thing that is true is, in terms of the way you actually use this in practice, is what you quite often do. The ideal thing is you generate on good data, you generate the correct restraints, correct constraints, the appropriate constraints, and then you use it. What you should obviously do is look at the constraints that come out and sanity check them, and then make any adjustments by hand that seem appropriate. If you don't have time to do that, or don't have the inclination to do that, the other thing that you can do is generate them and then run new data through it and look at the ones that fail, and that gradually tells you which ones you might want to write. So in this case, for example, that would tell us that the max constraint isn't appropriate and we might want to take it out. Obviously, you have to use judgment about that at that point about whether to take it out. The thing that you don't get that way is things never tighten. So if you turned out to have bad data, like you had a null in a field that's not supposed to have nulls in, obviously the null constraint won't get generated, and nothing you do in the future is going to force that, unless you try regenerating constraints on newer sets of data that maybe have been cleaned up, at which point you might get tighter constraints. And one of the differences in our commercial version of the software is it explicitly knows about bad data, and it will generate constraints in a more forgiving way that says, well, there are only one or two nulls here, so I'm actually going to say there shouldn't be any nulls at all. And, we have got some 10 billion and some minus 300 million values, but actually most of the data is between 100 and 200, so we're actually going to set those as the constraints. And in that case, of course, you potentially, if you verify the data that you built on, you now actually, if you're running it in that mode where it's allowing bad data, potentially it fails when you verify because it's finding the bad data for you. We're not necessarily holding that back out of pure greed. We might put that into the library, but it's newer functionality that we have. We tend to test everything in our own software first, and then when we decide it's good and working perfectly, we tend to put it into the libraries, and sometimes give tutorials a bit too quickly after doing that. So at the bottom of this slide it says pip install feather format. I don't know, people here heard of the feather format? Feather is a joint initiative between Wes McKinney of Pandas fame and Hadley Wickham of Hadleyverse, Tidy, RStudio fame, to make a format for writing datasets to disk that is interoperable between R and Python. And the idea with it is that it also preserves a lot more metadata than CSV files and therefore is better. It's not really designed for long-term storage, but for writing something out and reading it back the next day or an hour later or later in the same program or something, that kind of thing. It's part of the Apache Arrow project. It's quite nice. You can pip install feather format to get it. I say it's quite nice. It's quite nice. It doesn't really work. But apart from that, it's quite nice. Even more than Pandas, it has a very flexible approach to types. It's pretty confused about the difference between nulls and empty strings. It's pretty confused about nulls generally, actually. I think it basically thinks they shouldn't exist, and by the time you've written out a feather file, you should have done a fill NA or something. And partly as a result of that, we have a wrapper that turns out we haven't put onto PyPI, but which is available from GitHub, called PMMIF, which has the same method as Feather, but saves some extra metadata that allows things to be saved safely and restored more safely into Feather files. They're nice if you do want to have, not going through CSV files and not just using pickles to store stuff. They're a bit more stable and a bit more interoperable than those, so we've been using them quite a lot, and some of the reference data that we write we do use Feather files for, so it'd be worth installing that, and currently getting from the tdda account on Git the PMMIF format for extending that. That it might actually, 10 past 10, it's probably not available on PyPI by now, but by this afternoon it will be available on PyPI as pip install PMMIF. Okay, so what do we have next? Probably RexPy, I would guess. Oh, that's an example tdda file. That's what we've done. That's failing on 118, which I think we did. Oh, here's the brand new detect functionality that apparently doesn't work. So yes, exactly what we've been doing. So detecting is the same as verification, except that it actually pulls out the failing records. So you can use the framework as a kind of general purpose anomaly detector, if you like, or bad data detector, and not just know overall there's a problem with this column, but actually get the stuff written out either to a data frame or a feather file. Or a CSV file. Again, you've got both a command line version and the non-command line version, the API version. And obviously I'm a bit embarrassed about the fact it appears not to be working, but I'm sure it will be something trivial, and I'm sure we will get that fixed very shortly. And we'll tweet about it and stuff like that. So we've looked at that. Absent constraints, yes. So I'm sure you're all Sherlock Holmes fans and know the story of the curious incident of the dog in the nighttime, which is where Inspector Gregory of Scotland Yard says to Sherlock, my colleague Sam says I should never tell this story because no one ever understands it, but I think you'll understand it. Inspector Gregory says, is there any other point to which you'd wish to draw my attention? Talking to Sherlock Holmes, and Holmes says, to the curious incident of the dog in the nighttime. And Gregory says, the dog did nothing in the nighttime. And Holmes says, that was the curious incident, which of course proved that the burglar or murderer or whatever it was known to the victim, and hence the butler did it or whatever. So when you're generating these constraints, it's very important not just to look at the constraints that do get generated and say, are they plausible, but to look at the constraints that don't get generated. So if you run it over a master table with customer IDs and it doesn't say that the customer ID mustn't be null, what that's telling you is that there were nulls in the customer ID field. If it doesn't tell you that the customer ID has to be unique, that's telling you that there were duplicates in that field. And so, as with all cases of looking at data, it's very important to be vigilant and not do what we always want to do all the time, look at things and convince ourselves they're correct, but look at them and think of all the reasons why they might be wrong. So it will, modular bugs, it will produce the correct constraints for the data that you give it, but that doesn't mean they are the correct constraints for the analytical problem you're dealing with. Another important thing to say is This is not just about detecting problems with your input data. It's absolutely about detecting problems in your output data and your intermediates as well. So, if you're generating probabilities and it's running from like -4 to 13, that's not a great thing either. It probably ought to be capped between, I don't know, say 0 and 1 or something. And, if there's one thing worse than garbage in, garbage out, it's gold in, garbage out, right? You do not want to be the thing that introduces the problems into your data. So do use a dual points in the process. This is more stuff. This is about data frames, so you can do this off data frames as well as off CSV files. You can't do it on JSON yet. That's another thing that we might do. A thing that you can do that isn't talked about in the slides is it will run directly against data in databases, both for discovery and verification. So I think we currently support... What do we currently support? We definitely support Postgres and MySQL and SQLite, and I think we now support SQL Server and Oracle, probably. And that list keeps growing. So that's powerful as well. You can convert the set of results itself into a data frame so that you can end up with a data frame that shows you which constraints passed and which constraints failed, which can occasionally be useful, particularly for reporting. And there are lots of things coming. But what I think we'll finish by doing is talking about RexPy. So there are some contact. So actually I will. So if you want to get in touch with any of this stuff, those are my details. There's a blog at tdda.info. The source is on GitHub. There's a Slack channel that you can ping me and we'll add you to. It's a very, very quiet Slack channel, but it would be lovely if it became noisy. So do make it noisy. It's got its own tdda account, and I've got a tdda account, its own Twitter account, and I've got one of those too. The slides from last year are at that URL, and the slides from this year, once they've been slightly corrected, will get put up at the 2018 copy of that this afternoon, probably. And finally, RexPy. RexPy is part of tdda. If it says anything about doing them anywhere else, don't do that. There's an online version of RexPy as well, where you can type or paste in, I don't know, up to 1,000 or up to 10,000 strings or something that will generate regular expressions for them online at Heroku. So, regular expressions. God, doesn't it have the joke? Can't believe it doesn't have the joke. You all know Jamie Zawinski's thing about, some people when, it was his signature, wasn't it? Some people when they see a problem think, I know, I'll use regular expressions. Now they have two problems. Regular expressions are, does everyone know about regular expressions? Does anyone not know regular expressions? Fantastic. Well, you all know how easy they are to write. They look like this. I don't know why. In fact, I'm fairly sure there's a mistake on this slide because various people have told me that, but I've never managed to spot it. But anyway, they're sort of write-only type things, and even the writing's difficult. So the idea with RexPy is instead of you writing the regular expression, we get the machine to write the expression. There you go. There's old Jamie Zawinski. If anyone doesn't know about it, if you're typing these things into Python, for God's sake, use R strings, which means you don't need nearly so many backslashes. So yes, their pro is that they're powerful, and their cons are that they're ugly, they're hard to write, they're harder to read, they're harder still to debug, and they're quite hard to escape if you don't use R strings. There was a fad for a while to replace them with things called verbal expressions. Got implemented in about 3 weeks in every programming language under the sun, and I've never seen anyone use them since. We all go back to regular expressions. So the idea is to let the computer do the work. RexPy does it. So if when you're in fact, let's do that. If when you're generating your constraints, and if you don't have like paragraphs of text, which will then take the lifetime of the universe for it to work through, if you say tdda discover test data / elements, well, let's do it on 92. Elements.tdda, and you say --rex, I think. it will also generate regular expressions. And if we look at elements.tdda, so you can see it has figured out that chemical symbols are a capital letter followed by a lowercase letter, which is true. No, it's not. No, sorry, a capital letter followed by a number of lowercase letters, which is true. And it's figured out that chemical symbols are a capital letter followed by, no, a mixture. Okay, so it's not perfect, but that it's one or two, up to 92, it's one or two capital and lowercase letters. Now, ideally, it would obviously say a capital letter followed by a lowercase letter, but it turns out this is quite tricky. And what else have we got? Chemical series. It's found 3 different patterns for chemical series. It's not very good at repeated fragments at the moment, or repeated capture groups, but it can do that. When it generates them, RexPy, you can tell it to put capture groups in for any of the bits that are not constant, so that you can then pull them out afterwards, which is also quite powerful outside the context of tdda. So we can do this. We can also, from the command line, just, I think, yes, we can just type RexPy and either pipe stuff into it or put things in. So, a typical thing would be to sort of put in, the kinds of identifiers we tend to get. And 45 or whatever. And even for simple things like this, that should be enough. It will generate an appropriate, or sometimes an appropriate regular expression. In some cases, it doesn't generate a single one. It generates a set of regular expressions, and it will check that at least one of them is true for each string and report the results. It's definitely still a work in progress. I mean, it doesn't... one of the things to say about it is it's a purely heuristic method. It's not got a quality measure. It's not guaranteeing or even really trying, except sort of implicitly in the programming, to find the optimal string, whatever that would mean. And of course, the optimal expression isn't really well defined. In our heads, we know that we'd like it to be the one that captures all the stuff that's good and excludes all the stuff that's bad. But given that we don't know the universe of strings that exist in those two categories, it's kind of hard to do that. So it's gradually improving over time. We're close to having something to allow us to do the repeated fragments that I think will help quite a lot. But even now, I guess the thing to emphasize about it is what it's really good for is the sort of categorical strings that you tend to get that have structure in real data sets. What it is completely hopeless for, and it will take stupid amounts of time if you feed it, is like English sentences and English paragraphs and stuff like that, where clearly there is no sensible pattern for it to generate, but it will carry on trying stupidly anyway. So that's RexPy and how we're doing. It's 10:20, so we're quite close. So I think we'll have a look at the slides and see whether there's anything else. Oh, that's the online Heroku version. But you can download it and install it. There are a set of options you can specify. So you can help it a bit by telling it if you've got identifiers and underscores are really being treated like letters, it's helpful to give it a -u, and then it will do that. If dots are supposed to be treated as part of identifiers, you can tell it that, and same with minuses. You can specify whether you want it to put the brackets in for capture groups. And one of the other things that's happened over the last few months is it's become much better at handling Unicode. So it will generate rather cryptic regular expressions, but correct regular expressions even for accented characters. I don't know whether people have come across the... and it works in Pandas, yeah. I don't know if people how familiar people are with the -w operator in regular expressions, but -w, and in particular -W. So -w, I always thought matched a word, but it doesn't. It matches an alphabetic character in the alphabet that you're in. In other words, it will cope with accents on letters as well. And underscores, annoyingly, which usually you don't want. And digits, which usually you don't want. But if you use minus capital W, which means everything that isn't that, and then you reverse it with an up arrow in a bracket, and then you take out explicitly the digits and the underscores, you actually get a Unicode character. And so that's the trick that it uses when matching Unicode letters, well, international letters, accented letters, which turns out to be very powerful. It just makes for rather ugly regular expressions, but it works remarkably well. I think that's me, unless anyone has questions. Yes?
So for the regular expression bit, how do you guard yourself against overfitting? Meaning that if I have the first letter to be a 1 in my full data set, but it's not a necessary condition, it gets explicit in the regular expression.
So, I mean, in terms of the algorithm, the way it guards against it is, it's all just heuristic anyway, so it's just trying to do its thing. In general, I would say when you're using it in practice, what you do is you run it, you see whether it generates something useful, and if it doesn't and you can see how it's failing, you put in an example that will stop it doing that. So if all your examples start with a 1, then it's doing a really good thing if it produces only 1s in them. But if that's not what you want, put another, copy the last example, replace the 1 with a 2, and now it won't.
Okay.
It's not a great answer, but it's the only answer I've got.
Yeah, I see application to on data sets that you might want to alter yourself.
Yeah.
Maybe that's what you want to do.
Well, I mean, the other thing is obviously edit the regular expression, but then you're back into the hell that we want to avoid. I mean, it's not magic. It's just a heuristic. Yeah.
Somewhat related, it would be really good if you could put into data sets one where you would like the results to match and one where you would like it to fail.
That would, yeah. So if people can't hear, the suggestion is rather than just giving it the positives, the things that you do want to match, you should be able to give it the negatives as well. And we have thought about that, and that's a great idea. You could submit a patch with that, and if you don't fancy doing that, I'll add it to the to-do list for later this afternoon. Yep. No, it's a good idea. Any other? Yes.
When you work for a client, how hard do you have to fight to free up time to write tests? Does it take a lot of convincing?
I think you misunderstand the consultant-client relationship. We don't ask the client for permission to write tests. We write the tests, and if they complain we're taking too long, we explain they don't understand what they're talking about. No, I mean, there is, more seriously, there is... I don't think I know anyone... I've been advocating automated testing for at least 15 years. I don't know anyone who doesn't find it a struggle to do it. I myself, if I just want to get something done, tend not to write any tests in the naive and stupid belief that it will be faster than that, even though I know it won't be faster like that. It will actually be slower because I'll make mistakes that will take me longer to fix. I mean, my very firm belief is that writing tests isn't, it's not some frill. It's not something that you only do if it's a really important project. It's the fastest way to get code working in general, I think, and it is definitely the only way I know to get results that I have any level of trust in at all. So if a client really said, do it without the tests, I mean, I would either refuse to work with that client or I would write them anyway and just not include the tests in the deliverables or something. But in practice, we do get the pushback, but it's usually not all that hard, and we're sufficiently inflexible about it that it always goes away. And we've never actually had a client say, well, if you're going to insist on writing tests, you're not the consultants for us. Do you have the opposite experience?
I'm not working for consultancy, but
Right.
in general, if you sort of have non-technical stakeholders in a project, it's sometimes hard to justify to spend significant amounts of time on testing.
Yeah, but it shouldn't be hard to justify taking less time for the whole project because you're spending some of your time on testing rather than all of your time on wondering why stuff isn't working, right? You just have to believe it sufficiently strongly. The other interesting thing for us is our software, Miro, our proprietary software, is about 300,000 lines of Python. and until very recently it was 300,000 lines of Python 2 with UTF-8 in the middle rather than Unicode mostly. And as some of you may have heard, come 2020, that's not going to be a great position to be in, so we've been going through and in fact have converted it all. And I think that would have been completely impossible for us to do if we didn't have over 1,000 tests with over 15,000 test cases, which is what we do have for that software. Especially given that the approach we took was we tried to make it work and succeeded in making it work. The same source work in Python 2 with byte strings, in Python 2 with Unicode literals, and in Python 3, obviously with Unicode literals. But it's only because of the tests. When we first started running it in Python 3, I think like 970 or whatever of the 1,000 tests wouldn't pass, and I don't remember the number of test cases, but it was absolutely staggering. And in fact, one of the interesting things was we found about a dozen bugs in the Python 2 code just from the process of trying it in Python 3 and looking at the thing. Not that we ever write bugs, I would hasten to add. Any other points? Yeah.
I have a question about tdda and constraints. Is there any support for time series? For example, like a certain date missing between the ranges of dates or something like that?
Okay, so the question was, is there any support for time series? No, there's not. Time series or ranges of dates. So I guess the generalized version of that question would be, rather than having a continuous string, a min and a max, having a sequence of mins and max. So there is support in the sense that you can have date fields, and it will handle those appropriately. And I think we haven't put this into the open source version yet, but I might be wrong. In the proprietary version, we also have the concept of relative dates, so dates relative to either today or a reference date rather than the absolute date range, so that as stuff flows forward. It's possible that is in the library, but I don't think so yet. But it will be. It's definitely not being held back. So the more general thing, of course, is a sequence of overlapping ranges, which we have for strings in effect, because you can list a set of strings or a set of regular expressions. We don't have that at the moment. The other thing you can do, of course, is, and in fact a very powerful thing to do, I should have mentioned this, and I'll be talking about anomaly detection this afternoon, which uses this library for, or some of what I'll be talking about is using this library for anomaly detection. A very powerful thing, of course, to do is just to write your own constraints, your own checks that build extra columns in the data set that are either 1-0 columns or anything that the constraints that it does do have a sensible effect on. And then you can just feed those in. And I mean, sure, you're doing the work, but you get the nice integrated framework where the records that fail your extra checks fail these as well. And in fact, the other thing I should have mentioned is another very useful thing to do is not just to run tests on a particular data frame, but also on things that you derive from that data frame, like a crosstab that you produce that counts the number of occurrences and things and so forth. Tests on derived artifacts or aggregate data sets or whatever that come off your data sets, or that join data sets together, or any of those sorts of things. Right? Again, if you have two data sets and they're supposed to have common join keys, join them together and then check for the null. You don't have to do a new thing. If there are nulls in that, provided that you do an outer join, if there are nulls in the key field in the join thing, then you know that there were bad join keys and so forth. But the short answer is no. There's no real support for that. We done?
Yeah, I think we have to stop now because otherwise you guys will miss the coffee break. So I should say Nick is giving another tutorial this afternoon, right? Is it at 1:30?
Oh, I don't know what time it is, but it's on anomaly detection. It's
on anomaly detection in the afternoon. And I should also say that Nick will need to give this tutorial this morning on specific data analysis at short notice because someone else couldn't make it. So thank you very much for helping us.
Thank you. Apologies for the fact that